Alright, time for another DraftPhysics.com, debatephysics.com also, video presentation. So a couple of dopey comments, and I'll try to explain again. Yeah, it's just no point. But anyway, take a rubber band, you can stretch it with force and tie it around something larger like my tissue box. Yeah, you have your own little tissue box. How special. Anyway, the result is something being held in place with force without any momentum being present. And the argument is, of course, there's momentum in the force. The force is applying a constant pressure. So let's say you put it around an empty tissue box, and then you poured water on the tissue box, making the cardboard softer, and then you would see the rubber band start to move the cardboard. So clearly the force is present, clearly the pressure has been created, and the whole point is until you can move something, until the rubber band breaks, or until the tissue box yields, the force is being resisted. That is, it's just reflecting. The tissue box is elastic. It's saying, okay, you can press on me and I'm going to press back. You put pressure on it, it pushes back, just like the earth is doing to you right now. The earth is constantly restoring your position because you're constantly imposing yourself to the surface of the earth. You're applying, constantly pushing pressure into the earth. The earth pressurizes, the extra pressure pushes you back up. All right, so the motion is stuck doing this. So until the motion does this, or does that, or does something in some other place, it can't escape. It's stuck. Okay, and that's all you're demonstrating. Now, clearly, what happens to your motion over time, okay, is the fact is the pressure keeps going into the earth. Okay, it keeps moving into the earth. So it's only the constant pressure, the right now pressure, that's oscillating. So there's, it has to escape, and if it does escape, when it does escape, you'll see the rubber band restored to its original condition, and it'll stop applying the pressure. So when the pressure makes something move, it's used. That's how all energy dissipates. It's sort of all gets converted into what you could call heat, or microscopic movements. And then again, gravity recreates the big object capable of moving big things, like volumes of water in a geyser, or volcanic lava, and all kinds of other kinds of ways that it converts tiny motion into bigger motion. So yeah, I just don't, there's no, so okay, so the other guy's comment is related, so I might as well do that one too. But the whole point is that you have to use a force, okay, for the force to dissipate. It has to somehow be able, the pressure has to be relieved. And if you maintain the pressure, it doesn't mean the pressure went away, it doesn't mean the momentum is gone, it doesn't mean any of that stuff, it just means that it's reflecting. It's, the compressed ball is probably one of the best examples. The ball compresses. If I don't allow it to reflect, so I let it compress and then I hold it, you can understand that the pressure's stuck inside the ball. And until something moves, it stays in there. The little pieces of crap inside the ball are going to keep pushing on the outside, saying we want freedom, the compressed air. And even the rubber itself is probably, I don't know what percentage of the elasticity of a tennis ball is based on the air trapped inside the ball or the rubber of the ball itself, but obviously the ball works better if it has compressed air in it. So 50-50 or something like that. So the air is creating elasticity, it pressurizes because you're pushing it into a smaller space. And then the ball itself elastically expands, which again creates more storage of pressure. So it's just storing the pressure versus releasing the pressure. How else? I really shouldn't have to say it any other way. That pretty much, energy can get trapped. And when it's trapped, it's not energy. It's just trapped. It's oscillating, or it's going in a circle. It's trapped. All right. Okay, so Bobbly Boo just does the same shit all over again. So more crap about these stupid force sensors. All right, so look, here's some more force plate experiments. Okay, so this one was by basically a company selling these stupid things, and so again, he's making this argument that somehow something that weighs a half Newton somehow weighs 100 Newtons when I drop it, whatever, a meter. He didn't really drop it a meter, but whatever. So this gigantic, humongous amount of pressure, like that's whatever it is, 40 pounds or something. No, the tennis ball does not weigh 40 pounds. It's ridiculous. All right. So this was another video by high school kids, who knows. It might have been college, but poor quality, can't really see anything. And again, the argument is they have a basketball hit the scale, and the basketball weighs 200 pounds. So they drop it about a meter, a little bit more maybe, 200 pounds. It doesn't weigh 200 pounds. Okay, it never weighed 200 pounds. It's not possible for it to acquire 200 pounds worth of force. It can't manifest 200 pounds of force. The ball itself doesn't get compressed air inside of it that increases by 400 times. That can't happen. All right, so I will attempt to... he ends it with, I still don't believe. Yeah, of course I don't believe. It's crap. All right, so let me see if I can see this. All right, we'll get rid of this thing. It's in the way. All right, so like with gravity, you can make a gravity argument by saying any object that you're put in gravity, you can really understand it as just being elemental substance. So you could argue that this thing isn't being affected by gravity. The little bits inside of this thing are really being affected by the gravity. And the little bits all have a consistent weight, the protons and electrons. And so what you could really understand is they're the things actually moving, and they have a pretty constant momentum in the sense that each one of them has to move at the same speed because they're all the same size. They're all going to collect the same amount of force. And the difference is that more of them means you have to collect more force. You have more of them to collect it. So they're just like little buckets, you could say. And each of them collect exactly the same amount of force. And the feather, okay, is going to have less matter bits. So it's going to totally collect less force. It's just like a size of a sail on a boat. It's a small sail. So it can't catch much. Big sail catches a lot of force in the end. So in the end, all that's going to matter when they hit the ground is how many of these things are there and how fast are they moving. And so obviously they're going to move at the same speed, these two things. And then the only question is how many is going to decide how big an impact there is. So the impact is completely decided by the mass, because the velocity of each little bit will be exactly the same, and the energy of each little bit will be exactly the same. And all that's going to matter is which one has more little bits of energy when it hits the ground. And so the same thing is true for a volume of pressure. You can just understand it as being the little bits, the mass is going to decide. So if I have a big balloon, all right, I could fill it with 10 pounds of pressure. And I could have a little balloon and fill it with 10 pounds of pressure. And okay, the argument would be, all right, they're both applying 10 pounds. But obviously the big balloon is going to apply the 10 pounds for a much longer period of time. Okay, it's going to be able to produce little bits coming out of the balloon many more little bits because it has a greater mass, volume of bits. All right, so that's all that can be transferred. So this whole scale argument, what they're doing is they're taking a reading and they're assuming, it's this Newton seconds thing, okay? So they're projecting what the mass would be if it was applied over an entire second. So they get some idiotic peak like this for an impact. All right, and that peak is in 1/100th or 1/1000th of a second. And what they're doing is projecting what the newtons would be if it was for 1 full second. So if it happened for 1 full second, it would be 1200 newtons. But it didn't happen for 1 full second, so it's not 1200 newtons. So that's the bullshit of this. But something can't make more pressure. All you can do is change how, all you can do, you can't make the peak any higher. So if something has 40 pounds, then the 40 pounds will be here, and you can collect the 40 pounds in any kind of way. You can collect it all at once, very quickly, or you can collect it gradually, all right? But there's no such thing as I can make it make more pounds of pressure. So the balloon, pressurized, can only produce a certain amount of pressure. There's only so much pressure in the balloon. I can only make it produce a certain amount of pressure. That's all it can create. Can't create any more pressure. Now, the fact is I can accelerate particles out of it, okay, at a higher velocity, okay, and a smaller mass, but it would equal the same total pressure in the sense of it's still the same. If you do the mass and velocity, the momentum, you can't change the momentum. And so the fact is you can't make a basketball weigh 200 pounds by dropping it a meter. It just can't weigh 200 pounds. It can't physically create 200 pounds of pressure. And so obviously this reading isn't really, okay, the momentum or the weight, okay, of the actual, what was actually imposed on the scale platform. So the other argument you have to understand is the scale, the basketball hits the scale, okay, I need more room. It's not really weighing, okay, it's not really interacting directly with the basketball. So you have to understand it's transferring its pressure to a surface, and then that surface is doing the moving. So there's a platform, and they probably have 4 sensors on it, and in each corner. And so they're dividing, they figure out how to do the voltage change for each sensor and create a reading for the total amount of impact. But this whole platform is what's doing the moving. So the basketball transfers its energy to the platform, and then the platform pushes on the sensors. So you have to, it's just a practical fact. And there's no way the basketball can transfer 200 pounds of pressure to, of momentum to this object. It can only transfer its momentum, which is probably like 8 pounds. Let's see, a meter would be, if you start with, the ratio is simple enough. You start with 1. You go 1 centimeter, you weigh twice your weight. You go 4 centimeters, you weigh 4 times your weight. You go 16 centimeters, you now weigh 8 times. So 16 centimeters, and then it gets 64, is going to be 16 times your weight. So you know that to get, obviously 4 times 64, you're going to end up with this 2, whatever it is, number, 56. Is that right? Well, anyway, yeah, 6 and 6 is 24. Yeah, that's right. All right. That'll double this again to 32. So you know that 1 meter is going to be somewhere, in here. So you're talking 20. So you'll weigh 20 times your weight when you fall 1 meter. And the basketball just weighs like, 200 newtons. So there's no way it can weigh 200 pounds. It's just not possible for it to do that in that amount of falling distance. Yeah, so you're going to understand, that's all it can transfer is the total motion, the momentum, and all you can do is you can stretch it out or you can do it really quick, but it doesn't matter. You can't do better than this peak amount of pressure. There's a peak pressure that you'll eventually apply when you finally stop moving. So when you stop moving, the thing hitting stops moving, that's when all the pressure has been released from the object and is now in the other object. But it can be gradually collected, or it can be collected in a microsecond. And but all this peak is all there is. There's nothing more than that peak amount of pressure, and then it's all downhill from there in terms of whatever the elastic reaction is going to be, or some other vibration or something else. So you could see that in the silly experiments that he linked to, that in all of them the thing happens, the event happens, the basketball drops and you get this insane peak, and then you get this stuff, okay? And it's significant. It's about that size. And this is all vibration in the scale. It has nothing to do with the ball's gone. This is the scale vibrating. And so we're supposed to believe that the scale is vibrating with 10 or 12 pounds worth of energy. It's not vibrating with 10 or 12 pounds worth of energy. It's ridiculous. So obviously this is how the scale is interpreting any action. So at each point it's just doing this per second thing, okay? So every tenth of a second or hundredth of a second or thousandth of a second, it's making a reading, okay? And so it's just, and each one of these readings, it's superimposing as if, what if this was a full 1 second? How much pressure would that be? So if it did that for that amount for 1 full second, how much would that volume be? And that's what it's reading. It's exaggerating each one of these points because it's presuming it's a full second worth of that amount of pressure. And so that's why it's recording this idiotic number, because it's doing Newton seconds. It's not doing newtons. It's doing Newton seconds. All right. Yeah, that probably should be enough. I guess I'll just pursue the elemental argument one more time. And so you can understand, look, if you did have one atom going 1,000 miles an hour, right? And you pushed it into a bunch of other atoms. Okay, so you have a bunch, 1,000 other atoms. All right, you can understand that all it can do is transfer. All right, so it hits one of these other atoms that has the same mass as it. And what's it going to do? It's going to split the motion, right? You could argue. Or, it's let's say if there were Newton's cradles, then you'd end up with, it would just keep transferring, hitting. So we're going to hit more than one object at a time. So let's just say it's like pool balls, and they're connected in this manner. So when you hit this one, you move these two. So then you can understand, now you've cut the speed in half, right? So let's just make this 100 to make this easier. So now you'll have 50 here and 50 here. And then you do that again, and you cut to 25 and 25 and 25 and 25. And you just keep doing that. And you can understand that I can just take this 100 velocity of this one, and I can basically turn into 100 things moving one. And those two things are going to be equal. One can create the other. Now it's a lot harder to take the 1 mile an hour and somehow force it to become 100 miles an hour. At the top of my head, I can't think of anything simpler than just applying the lever to do it, because everything else doesn't seem it's going to be as easy to do. So I guess I could pause and try to think of some way that you can convert slow motion into fast motion, besides using a lever or gears or some other mechanism. So anyway, but you can get that you can do it this way. And this is sort of the bowling pin argument, that, you know, there's no way that the 8-pound bowling ball can do any more work on the pins than the 16-pound ball. So you have the 16-pound ball, the 8, this one's going 16, this one's going 8. So they have the same momentum. Your silly theory says that this small ball has twice the energy, twice the ability to do work. Okay, so I put up the pins here, and the fact is, okay, that it will not transfer to the pins any more momentum than its momentum. It can't give the pins any more than just its momentum. So in the end, you're going to have the same amount of mass moving a velocity in both cases. These two numbers are going to be exactly the same. So in one case, you're going to have more pins moving slower, and you're going to have less pins moving faster. And that's all you're going to have. There's nothing else here. Nothing else will be transferred, because all this can do is hit a pin, give it its momentum. It can't give the pin kinetic energy. It can only give the pin the momentum it has. That's all it's going to. This is going to lose This is going to lose a vector of momentum that'll be exactly equal to the vector of momentum it gives to the pin. So every time a pin flies away with whatever momentum it has, the ball has that much less momentum. So you can understand when the 16-pound ball going 8 hits the first pin, it can only give the pin 8 miles of velocity. Can't make the pin go faster unless you make the pin out of rubber or something. So unless you put a spring on it. So that's all you're going to get is 8, right? So you have a mass of, say, 3, and you have a velocity of 8, and that's what this has to lose in momentum. And the first pin the fastball hits, well, that can go 16 velocity. So it's a 3 times 16, so a big giant chunk of momentum will be lost with the first pin strike. But in the end, it's going to be exactly the same mass and velocity moving. The same total momentum is all that will be exchanged. So there'll be no sign of the 8-pound ball going 16 moving more matter. It can't move more matter. It can't move more matter, more MV. You're still just stuck with that idea that it can't apply any more motion than it has in terms of its momentum. So yes, you can make something go faster. You can make one thing go fast, or you can make 10 things go slow, but it's always going to be the same MV in all the transfers. So kinetic energy plays absolutely no role in any transfer, because you will not transfer the kinetic energy, and that's what's found in all the experiments. All the experiments demonstrate that kinetic energy isn't conserved. Every single one of the real experiments. Now, they do claim these fake experiments where they do this subtraction math, and they actually create, 3 times the total momentum. But these are not real experiments. They don't really happen. Okay, so we don't have any clinically decent experiment demonstrating that you can plow a 1-mass object into a 3-mass object. So let's say the 1-mass object has 100 momentum. Their claim is this will leave with 150. So I'll gain momentum in the direction it was moving. It's moving in this direction, this is moving in this direction, and it gained a big giant hunk of momentum. And the small object will reflect, okay, even though it gave more energy than it has. It gave more momentum than it has to the object, and still it will reflect with 50 going this way. And their claim is that you conserve the kinetic energy because you subtract this from this, or conserve the momentum anyway. And it's just a nonsense. It doesn't happen. Complete fake, phony, fraud bullshit. So This was the experiment physicist Michael was supposed to do, and then he went silent on the internet, without producing the experiment. So anyway, all right, that's probably enough. I'll take a pause and see if there's anything I need to add. But anyway, I could go through all the ballistic pendulum, I could go through the lever, I could go through gears, go through water pressure, go through hydraulics. Let's see what other arguments there are. And the kinetic energy is not to be found. And again, the simplest thing to state is, in their 350 years of their claim of this stuff existing, and their claim that a 5 mass going 10 velocity is twice the energy, okay, of a 10 mass going 5 velocity, okay, and they never did the experiment. They never, did a tug of war. Send this off this way, send this off this way, let them force them to compete with each other, and by their theory, of course, the 5 mass should decisively win. And their theory is that actually a 20 mass going 5 is equal. Okay, so they're saying that if I did a tug of war between a 20 mass going 5 and a 5 mass going 10, that will be a tie. And obviously this is going to the 20 mass is going to decisively win. So if I had real cars, they could do this with anything, right? They could do this with any kind of object, a truck against a Volkswagen, whatever. And the fact is we know momentum's going to decide who has more energy. And these kinetic energy numbers won't mean a damn thing. I mean, I've already done we already landed on the moon thing, so I could make the moon argument over and over again, that thrust only obeys Newton's third law when you calculate the momentum of thrust. If you calculate the kinetic energy, you won't get an equal and opposite reaction. The lunar module will not move with the same kinetic energy of the thrust you calculate, but it will move exactly proportional to the thrust calculated as momentum. And those simple facts are just so decisive. So again, why don't I believe? Well, I don't believe because it's junk. It's garbage. Your theory doesn't make any sense. It doesn't fit. It doesn't work. It doesn't produce any accurate results. It doesn't produce any accurate predictions. It's not the most predictive theory in the history of mankind or any of that crap. It's rubbish. It fails every reasonable, fair test. It fails to display its usefulness as a fact because it doesn't get right answers. Shit. Okay, now it's enough of a video. Probably. Well, I'll pause and see. I guess I'll just throw in some extra commentary. So, as I have repeatedly mentioned, okay, this all started with Leibniz making the claim that 4 pounds dropped 1 foot is the same energy, the same impact pressure as 1 pound dropped 4 feet. And the lever decisively proves that no, a 1 mass has to go 4 velocity to equal a 4 mass going 1 velocity. So the lever makes a completely different argument and demonstrates a completely different truth. And you've never tested Leibniz's theory. So you've had 350 years to do the experiment and they've never done it. So you can understand, oh, come on, this is the definition of your science. You have 350 years to do this simple tug of war or to drop these stupid little weights in some sort of clinical way and measure how much capacity to, move pins. Instead, you do experiments that, well, they don't even do that. They don't even explain things like the fact that you can slide over thin ice quickly and not fall in. And they don't have any rational explanation for why that's a fact, except for the simple truth that you weigh less. The faster you go across the surface, the less pressure you're putting on the surface, the less contact, the less capacity to push the ice, because you're collecting less gravity per inch of space you're applying your gravitational pressure to, because you're not on it long enough to weigh your weight. You've defeated weighing your weight because you haven't collected enough force over the distance to weigh your weight. So that's simple. What else? It's just, it's junk science. I mean, 350 years to prove a claim, and they haven't bothered trying to prove it. They haven't provided any clinical experiment that demonstrates that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet. And then they're going to claim to me that I'm the unreasonable one, when they're selling a theory that they haven't even bothered to even do any of these experiments. They haven't crashed cars, they haven't done any tug of wars, they haven't done anything to prove any of this. How is it not just dogmatic religion? They say it's true. They don't show you it's true. Okay. So, until the next time, and you fall for it. You don't even care that I just made these arguments. You just say, no, it's okay. Scientists don't have to do experiments. They don't have to test their theories. It's okay. They just tell me what to think, and I'll think it, because they say so. I mean, that's what you're saying to me. And it's disgusting.